Okay, thank you for being here in spite of the weather. Okay, just to remind you, we were dealing with the three-level atoms, so it was J equals 0 to J equal 1 transition with one field which was sigma plus polarized and the other one which was sigma minus, and they were contrapropagating. And in the low saturation regime, I can just add the two forces, and then I can make the expansion considering that the small delta is much smaller than the large delta, and so this one contains the Doppler effect and the J mu BB, the Zeeman effect. And so I make the expansion of this expression, and I have a friction coefficient, a friction force, and a restoring force with a spring constant. And so this is the expression I have. So it is a friction coefficient if alpha is positive, which means that delta has to be negative, so you have red detuned MOT. And so if you work with the constant laser intensity, then you see that the friction goes down with the detuning as 1 over delta. But if you increase delta, you are allowed to increase also the intensity, because the saturation is the intensity divided by the detuning squared. So if you want to work at larger detuning, you can play with a constant saturation, and in which case you just have a 1 over delta decrease in the friction coefficient. So I clearly stated that it is valid only in the low saturation regime that you can add the two forces. And so if you want to go to high intensities, then you have to play some tricks. So this is just, in fact, I will not make the full calculation because it is straightforward, but it is a bit lengthy. So if you go to the rotating frame, so in the rotating frame, it just means that instead of considering the excited state, you consider a strange object, which is just have the I omega L T inside of it. And so with this, in fact, you follow the evolution of the electric field in the complex plane, and the evolution of the atom becomes in the low frequency. In fact, you subtract the optical frequency in the, and then what you have is that your Hamiltonian, if you just put the ground state here, so it is 0, and you have the two excited levels, so, sorry. And you have, because you are in the rotating frame, you just have the detunings with the minus sign because it is the excited level. So you have no coupling between the excited levels. And you have here the two Rabi frequency. And if you are not scared with complex number for the Rabi frequency, you just consider them as complex number, and here you have the conjugate. So this system you cannot solve because you have here two different frequencies and you don't know how to deal with them. But what we are interested in is in fact the limit where the small delta is much smaller than big delta. And so here, delta plus is delta, big delta minus small delta, or plus here, and here it is minus small delta. And so what you can do is just to split the Hamiltonian between one 0th order and one 1st order. And so the 0 order is delta equals 0, and here you keep the linear term in small delta. So if you look at the 0th order Hamiltonian, in fact it is very nice. So omega plus, omega minus, minus delta, 0, 0, omega minus star, omega plus star. So this is very nice because in fact it is the usual two-level system. To see that, the simplest way is just that you have your three-level atom with the coupling sigma plus here, sigma minus here, and so if you assume that the two have the same intensity and the same frequency, which is the case here, then you can change, instead of taking the quantization axis along the z direction as we did here, you can switch to the quantization axis along the x direction, which is the polarization of the resulting field, because if you have a sigma plus rotating field and a sigma minus rotating fields, it just gives you a linear oscillating field. And so in this case, you see that this system becomes a much simpler and usual system where you just have one resulting field which is pi polarized in the x direction. And so this is a two-level system. You know it, and you know everything about it, because we did it at the beginning of the week. And then you just have to compute the density operator. You decompose it as the 0th order and the 1st order. You know the population at 0th order. In fact, they are just the usual sigma plus minus squared divided by 4, yes, 4 delta squared. So in fact, what you see is that your transition is saturated by both the two fields at the same time. But you have to compute this quantity, and it is not so simple, because now you have to take into account the H1 part, which is just a bit strange for perturbation theory, because you have a diagonal perturbation term, and only diagonal in this basis. But obviously, as I mentioned here, the proper basis is the Q quantum axis, and so you mixed everything here, and you have non-diagonal terms in your perturbation. And question, yes? In fact, here I write the problem taking the z-axis, which was the propagation of the beams, as the quantization axis. But I have no magnetic field, and I have the two electric fields in a given position, because I am also at rest, because I have V equals 0. in a given position, the sum of a rotating field in this direction and a rotating in this direction is just a linear polarization. And so this is the only direction that is given to my system, because I have no magnetic field. So I can choose that as the quantization axis instead of the z-axis, which was imposed by the magnetic field. So this is a bit strange, but you just have to compute, and you can just write the friction force as the result of the first order. And in fact, it is the same basic formula, h bar Ka gamma, and you just have the population minus the population of the minus level. And this is a bit lengthy, but straightforward to calculate. You have a first term that is identical to this one, except that now you have omega squared in the bottom. But you have also a correction term, which is rather complex. But if you go to very, very large intensities, with this kind, if you just add here an omega squared in the denominator, which is the spontaneous tendency, you have decrease of the friction coefficient as 1 over omega squared, 1 over the intensity. But if you make the whole calculation, in fact, the leading terms is compensated, and you have a quicker diminution of the friction parameter, and in fact it goes as omega 1 minus 4, so the square of the intensity, instead of going down as the intensity itself. Okay. Any question? No, so it's better. But so it is not difficult. It is just that you have to write things and not forget something in between. Yes? Yes? Yes.
But then, like in the experiment, you need like a phase relation between the two lasers? I mean, if you have lasers...
No, because so if the phase between the two lasers change, so if it fluctuates, it's in fact, you have the two lasers with the same frequency, so the phase does not fluctuate at the proper range of the time scale. So to do that, I need to have the frequency which are defined better than gamma, which is the typical time scale for the internal degrees of freedom to go to steady state. So if your phases of the laser fluctuates quicker than gamma, then it means that you have a very bad laser. And this breaks down. You have to have a good phase coherence between your... Yes, but this one will evolve with at the scale of milliseconds, and so you just follow. If you have the x axis, will just smoothly rotate a little bit or oscillate or doing strange things, but at on a time scale which is completely irrelevant here, and you will follow adiabatically. Your atom will adapt to the rotating polarization. Okay. Now I am very happy. I have a force, which is a friction force, and this I know that if I wait long enough, it brings everything to rest. But my atoms are quantum objects. So the question is, what happens? An atom cannot be at rest because it becomes a very wide object. And so the question is, what is the limit in temperature? So no, maybe this is just 2. So when I have a force that goes, so just consider the case where you have no magnetic field. You have a force that is minus alpha v, and so this means that in a time 1 over alpha, then v, so tau on the order, v goes to 0. But 0 is a bit pathologic, and so where did we oversimplify the problem? You have an idea? Yes, and why? And where do we drop the recoil? In fact, this force is the mean value of the force, and what we drop is the fluctuating part of the operator. And so if we want to know at which temperature we can cool our sample, we have to take into account this fluctuating part, which at one point will be predominant and will impede the velocity to go down to 0. You will end up with an equilibrium between the fluctuating part of the force that will eat the system and the mean part of the force which cools it down. Yes, maybe one point I have missed is to answer the usual question, where goes the energy of the atom when I cool it? To the field. To which field? No. Yes, in fact, the energy goes into the spontaneous emitted photons. And in fact, it is, when you excite the atom, it works also with the 2-level atoms. You are somewhere in the red detuned part of the field. So it means that it becomes resonant if the atom has a good velocity to come, so in fact to increase the frequency, but it will absorb a photon of frequency omega L, so it will gain the energy h bar omega L in the lab frame. But it is moving and it emits a photon at the frequency omega 0 in its own, in its frame. And if you convert in the lab frame, then depending on the direction of the emitted photon, it will have either the same frequency omega L or a higher frequency of the range omega 0. So this is the energy you give to the atom, and on average it will send you back an energy in the spontaneous, in the vacuum field, which is only omega 0. So the difference in energy you have taken that from the kinetic energy of the atom. Okay. Now we just, so the force just was the gradient of the VAL field plus the gradient of the VA vacuum field. I think it was this name. And so we have the mean force, but we have also to take into account the change, the force that is due to spontaneous emission, and so on. So to do that, we just consider that we have a Brownian motion, and we will have to consider the motion of the particle, so the change in momentum as the damping part. So to absorb the mass of the particle, I just put a gamma which is different from alpha. But you also have a fluctuating part which is described by a random force which depends on time. So this is a random fluctuating force. And obviously, as we have already treated the mean value of the force, that here you just have the mean value of F, mean value, which is 0, because otherwise you count it twice. To solve this problem, in fact, we have to know the time correlation of the fluctuating force. And so what we have to calculate is something t prime, which is the average value of f of t prime. And this is different from 0. So I will not calculate this completely because it is the quantum regression theorem, and so the mathematics is a bit heavy. But we are always interested in what occurs at an external, a typical time, which is the Tx, which is much longer than the internal time for the internal variables of the atom, which is itself much longer than the coherence time of the vacuum. And so for studying the external motion, we can just consider that the correlation t prime is just a 2D delta function. Because in fact, if you wait a time which is longer than the vacuum coherence time and longer than the internal variable settling time, then you lose all your memories about the fluctuating force. And so you have no correlation left for times on the order of gamma, for sure, gamma minus 1. And at that point we have almost finished, because so if we can rewrite this as 2D equal sum over d tau of f of t plus tau. And as we are in the stationary regime, this is just independent of t. Or you can, no, I have a minus sign here, I don't know why. But so, now we formally solve this equation just as if, sorry. So we formally solve this equation, and we write that we have the standard solution, which comes from the evolution here, the friction part, and we have to add something, which is the contribution of the fluctuating part to this. And so I have to integrate this on the past. I am looking at what happens at the time t, and so I have to integrate the force that has been seen at previous times, but I have also this force has been damped. The effect of this force has been damped, and so I have the evolution here. And so now what I want to compute is delta p squared, which is just the mean value of p minus mean value of p squared, and mean value of that. So I use both the bar and the bracket for the mean value. It is the same mean value, but it is rather uncomfortable to have twice brackets, or you have a long bar along a very long formula, and it is not so nice. And so you just plug this expression here, and you just have to make the calculation, and you find that the evolution is just going as 1 minus 2 gamma t. And if you wait long enough, then it will goes to d divided by gamma. And so this will be, in fact, if you start from any distribution, any initial velocity, you will end up with a dispersion of the momenta, which is given by d divided by gamma. And if we want to define a temperature in a 1D, because we are working in 1D, so we will write 1/2 of kBt is equal to 1/2 of this momentum spread divided by m, and it gives you within a factor of 2. I do not want to calculate a kBt, which is now the ratio of this diffusion coefficient, which has been defined like that, and this is the friction coefficient that we had in velocity. In fact, between gamma and alpha there is just a m, which is now disappeared here. Okay, so now we will try to have hand-waving arguments to compute this diffusion coefficient. So I was no, okay, this was brown A, now I am B, and so it is diffusion in momentum space. In fact, we want to have an estimate of this diffusion coefficient to have the final value for the temperature or the mean kinetic energy of our particles. So if I look at this expression, instead of going, so this was for times going to infinite. If I look at this expression for short times, which means that gamma t is much smaller than 1. In fact, it is t smaller than the tx. But I also want to have mean values at the atomic scale, so I will also consider that this time is longer, or at least equal to the internal time scale. Question? Because you have d over gamma here, and you have the m, and probably yes, the force is defined here as gamma p, and is defined as alpha v here. Two different alphas. Where do I have another alpha? No, this is the friction coefficient. It's just I didn't want to have here alpha divided by m, and so I introduced gamma, but it is alpha. So it's okay. So in fact, each time a spontaneous photon is emitted, the atom goes a change in momentum, which I can write it as Q, which is the difference between the K of the photon that has been absorbed and the K, the photon that has been emitted. Obviously, if the spontaneous emitted photon is exactly in the same direction than the absorbed photon, then you have no change in momentum. And so in principle you can have also some transfer of photon between the two beams, but because here we have chosen a situation where you have a sigma plus, sigma minus configuration, then you cannot have any redistribution of the photon between the two beams because they have different polarization. In fact, when you absorb a sigma plus photon, you are in this state, and you can do nothing with the sigma minus photons. The only thing you can do is either you turn back with a stimulated emission in the sigma plus beam, in which case for the momentum it changed nothing, or you emit a spontaneous photon, sigma plus photon, somewhere in the space, in which case you have here a difference in K. So now I have a random processes which consists in absorbing photons with a rate pi plus gamma for the sigma plus photons and pi minus gamma for the sigma minus photons, and always, so this is for a change for the absorption, but for the emission you always have also a spontaneous emitted photon. So if I wait long enough so that I have exchanged many photons, but not too long, so I do not change significantly my position and my velocity, then I can say that the delta P, the change in momentum, is just this KL, H bar KL, times the time I waited, because this is, sorry, gamma. So this is the number of photons that have been absorbed. This is the photon that, this is the photon that have been absorbed. This is the photon that have been absorbed. And here I have already take into account the fact that the spontaneous emission is isotropic, and I have scattered a lot of photons, and so the mean value has already vanished. But now, if I just want to compute the square of the variation of the square value of P, then I have to compute somewhere the Q, the square of the exchange, and KL squared plus K spontaneous squared minus 2 KL K spontaneous. So this is a scalar product. And when I want to compute the mean value among several events, then this one is constant, this one becomes mean value, and this one drops out, because again the spontaneous emission is the same in the opposite direction. So the mean value on several spontaneous photon is just dropping this term. So now it depends on on the wave, the mean wave vector squared for the spontaneous photon. And so if you consider the dipole emission for our 1D problem, then in this case you can find out that you have 2/5 of K squared. You know, a dipole emits more in the horizontal plane, orthogonal to its direction, than in the vertical plane. It is also related to the YLM wave functions that have been introduced by Yoke. And if you look at the diagram of emission for a linear dipole, it looks like the P wave shape for the but if you just want to consider the 3D problem, which gives simpler expression in a 3D problem, then you have just 1/3 for the mean value of the spontaneous momenta is just, no, sorry, it is just 1. Because here, in fact, you consider only the motion along one axis. So what is of interest is the projection of the spontaneous wave vector on that axis squared. And so you have to take into account. But in a 3D problem, it is just the usual wave vector that you have to take into account. This is just yes. So there are the population in the excited level here and in the excited level here. Because so this is the rate of emission of spontaneous emission. But to emit a photon with a sigma plus polarization, you also have to absorb a photon with sigma plus polarization just before. So this is also the number of photons. So the pi plus gamma t is the number of sigma plus emitted photon but it is also the number of absorbed sigma plus absorbed photons. And so here the spontaneous emission vanishes because I take many events, and so the isotropy of the spontaneous emission kills the contribution due to spontaneous emission, and I am left with the difference into the population times KL, which is just the usual radiation pressure force. This is just another way to have the radiation force. Yes. Yes. Yes, but it has the same probability to emit a spontaneous photon sigma plus or sigma minus in this direction or in this one. And so the mean value of the K spontaneous will disappear. And so what remains in the change in momenta is just the change in momenta due to the absorption process. In fact, here you would have a pi plus plus pi minus times gamma t times the mean value of K spontaneous. But this is 0. Maybe minus, but minus 0 plus 0 is the same. So. Okay. Okay, now what we consider, so a time interval, which was t, and the number of photons absorbed in the sigma plus light is just pi plus gamma t, or so plus minus. But this is only, you have the mean number of photons, which is in fact that. But when you have, so a mean number, the total of absorbed photon, which is plus pi minus gamma t. So this is the mean number of photons that have been absorbed in either the two. So it is the mean number of photons that have been emitted also. But this n is just also a random variable, because an atom can always choose to absorb a photon or not to absorb it, or absorb it a bit later or a bit earlier. And so when you have distribution of integer events, so you cannot absorb half a photon, you always have to choose either you absorb it or you do not absorb it. So n is a random variable which is not exactly determined, but it is a random, discrete random process, and so you have the Poisson law, which tells you that you have a spread in the value that you can have absorbed, delta n squared, which is just given by the mean value. And now I can compute everything. I am lucky. I can compute the variation of delta squared. So, which was, according to this expression, just 2dt for this. So this is maybe, yes, maybe I have to consider, no, it's okay. So now I have to take into account this number, which is the number of photons that have been absorbed, but only the fluctuating part of it. And so I have my delta n squared times h bar kl squared. And I have also the other contribution, which is the mean number of photon exchanged times the k spontaneous squared. So this is just that the number of photons that are absorbed in each of the beam is not known exactly. It can fluctuate with this delta n, which is equal to the mean value of n. And this is just the mean number of photons, spontaneous photons that are emitted, each of them contributing with this contribution here. And so if you now go to low saturation and you turn back to your favorite relations, then you will have omega 1 squared divided by 4 delta squared plus gamma squared. And so from this relation, you will recover the change in momentum, and you will have, again, you will use minus delta gamma omega 1 squared divided by delta squared plus gamma squared. No. Yes. And so, no, sorry. Yes. Yes, sorry. This is just the change in momentum here. Simply, this is just the part that comes from the absorption, but I don't know from which it is absorbed. This is a single event. So it is one absorption and one emission. And then here, yes. So, yes. Yes, so if we just put all together, we just have here, we just take this one, and we end up with d equal gamma omega 1 squared divided by 4 delta squared plus gamma squared, and no, maybe to erase something. So depending on whether you consider really this mean value for the spontaneous emission, or the case of the 3D, you have different results. And so in the books, you can find different results. If I stick to the 1D case, so this is the mean value of kz squared in 1D, in the 1D problem, then I have here a strange factor 7 divided by 4 h bar square kl squared, because 2/5 comes from here and 1 comes from there, and so it is 7 divided by 5. And so this, now you end up with the temperature. So usually I put some quotes in between, because the temperature is really strictly defined for a Boltzmann gas at equilibrium. And here we just have atoms that interact with photons, and this is not a priori Boltzmann gas. But people at the beginning were competing with the low temperature industry, where you have a dilution cryostat, and so they measure temperature in Kelvin and millikelvins, and so we take the habit to have a temperature, but in fact it is delta P squared, and it is D divided by alpha. And if you look, you just take the D and the alpha we had obtained, and you find that it is h bar gamma, a very strange factor, and dependence on the experimental parameters. So this gives you the scale, and you cannot expect anything else, because you are dealing with atoms which have a characteristic with gamma, and so the natural energy scale is h bar gamma. And this is just a strange factor resulting from the physics. And so if you look at the optimum for the temperature, so this is minimum when delta is equal to gamma divided by 2. And so if you look in the books, very often you find that for 3D, the KBT 3D, usually you find that the minimum temperature is just h bar gamma divided by 2, probably because this factor has been dropped in the case of a 3D not. Yes? From here, I have, so this is more or less what I take as a definition, because it is the expansion of delta P for short times. And then I just make my hand-waving arguments, counting the photons that are absorbed from here, the number of photons that are absorbed from there, and I have another estimate for the same delta P squared, which comes from the variation of the photons that are absorbed in the laser, which fluctuates, and the number of spontaneous emitted photons that is also which direction fluctuates. And so, in fact, as these numbers are both proportional to t, then from this relation I can get the expression of d. Yes, it is this. You take just the pi plus pi minus we have, and it comes here. You have this plus, so 2 divided by 5, and the gamma which comes here. So it is really to copy this into this. Any question? Any remarks? Okay. So we move on. Okay, and now let we start with the sub Doppler cooling. And so the predictions, let's start with a little bit of history, because it was back in the 80s and you were not born, so maybe I have to make some reminders. So the Doppler cooling is just what we have done at the moment, predicts that you have a minimum temperature, which is h bar gamma divided by 2. And if you look, you make the application, the numerical application for sodium, you will have a minimum temperature which is 245 microkelvin. And so now if you look to the experimental results, so it is Chu et al. And so this was back in the 1985. They measure very strange result. The measure value they gave was microK. So this is nice, it's the theoretical value. But what is a bit strange is that they put some error bars that allows to go slightly above this temperature, but mainly below this temperature. So probably they were a little bit afraid to contradict the theory, and so they gave, okay, well, in between, so they choose this value. In fact, they were wrong, but in fact, we will talk about the new mechanism that takes place, which is a Sisyphus cooling. And we will first talk about the experimental results of these good old days. So do you know how do you measure the temperature of a cloud of cold atoms? Yes, the experimentalist knows, the theoretician doesn't. So it's the so-called time of flight technique. And it is very simple. You just prepare your sample of cold atoms. So you trap them. So you have a nice small cloud of atoms, typical size less than 1 millimeter. And you just turn off everything. What happens? Gravity. Usually the atoms are just moving around with high velocity, they just collide every time, and so the gas is just in a steady state position. But when you have cold atoms and you release the trap, so you turn off the beam, you could turn off the magnetic field, then your atoms will just fall down. And if at some position below the trap you just put some light and either collect the fluorescence from the atom, or you just look at the absorption of your beam, then you will see your atoms that were initially here. You will see them going through the sheet of light, and so you will see the free-falling atoms at a height h below the initial the position of the trap. Yes, so yes, you can do it obviously now. So this is the technique at that time. Now you have more sophisticated techniques where you just release your trap and take a picture of it before it falls down. So you just shine again some light on it and you see the expansion of the cloud, but almost in situ. But for that to work, it is better to work with BEC, because the BEC is much smaller in size, and when you release it abruptly, it has also it expands also quicker. But here, so the technique at that time was just you just have 10 centimeters below or a few centimeters below, and so you have a mean free fall time which is just given by GT 1/2 GT T0 is the height you have to wait. But now if you consider here an atom, one specific atom which has an initial velocity v0 and a position, a vertical position z0, then you can compute you can write its evolution, and you just have so you just write that T for this particular atom is something, the mean value plus a small deviation, and so you have to write the equation for the atom. It is gt squared plus v0 t plus z0 is equal to minus h. So this is just the motion of your atom, and if you consider that the spread is much smaller than the mean value, then you can make an expansion of that, and you find that the delta t, so the difference between the average value and the time you see the atom in the sheet, is just given by v0 divided by g plus z0 divided by gt0. And so if you measure the spread in the arrival times so the width, if you have if you just measure the absorption of your beam, what you will see is that so at this time t equals 0, you release the trap, but obviously you see nothing because the atoms didn't reach the sheet. Then you see the absorption, and then all the atoms have fallen down, and so this is the T0, the mean time to reach the sheet of light, and you have the spread here, which is delta T, which is related to the delta V of your cloud, so the squared and the delta Z of your cloud. And obviously, if your cloud is very broad and the height is not sufficiently large, then you will have some problems because this component may dominate the velocity spread. And so what interests you obviously is this term here, which gives the temperature. Okay, so if you want to measure small temperature, you can also play tricks and have a double time of flight. And so if you have a double time of flight, you have two independent measurement of delta V and delta Z, and you can just kill the contribution due to the initial size of the trap. Okay, so we turn back to the experimental results. Maybe, yes, I have to keep this formula. So, back in history, you have the group of Bill Phillips, which makes some measurement, and they measure temperature down to 55 microkelvin. Yes, so this was for cesium, if I remember properly, and the Doppler temperature for cesium is slightly lower than for sodium. It is 125 microK. So clearly they measure temperature lower than the Doppler limit. They also observe that the temperature has the tendency to go down when you increase the detuning. If you look at this expression, you expect that the Doppler temperature will increase with the detuning for a detuning larger than gamma divided by 4. So this was one part of the problem. Then in the beginning of the 90s, at the ENS, they measured the temperature, and they found that the temperature increases linearly with the intensity of the laser. If you look here at the temperature, in fact, you have no intensity dependence. This is just due because to the fact that the diffusion coefficient is proportional to the intensity, but the friction coefficient is also proportional to the intensity. so the two dependence in intensity drops out, and the temperature do not. So the Doppler temperature do not depend. Sorry. Okay, so sorry. It is at the NS that they were paying. Okay, so just forget that. It was also sodium. So they are almost 5 times lower temperature than what it was expected. Okay, so we have a problem. To make the quotation, Houston, we had a problem. And in fact, the problem comes from the fact that what we have to consider here is sodium, cesium, rubidium, and all these alkali atoms have a very rich hyperfine structure. And for instance, the cesium atom is not a J. So, because the Doppler model, just recall, the Doppler relies on a G equals 0 to J equal 1 transition. For cesium, in fact, you are dealing with a 4 to F prime equal 5 transition, which means that here you have 9 sublevels, and here you have 11 sublevels. So in fact, you have to deal with a 20 level system. Okay, too much. And as you can guess, when you add some levels, you can play better tricks. So now B, which is the system under consideration. Because I won't treat 20 levels, it took 20 minutes to draw it, so it's too long. So we will consider just the minimum increase for J, which is J equal 1/2, and the same for J prime, which becomes 3/2. So in this case, in the upper level, you have 4 Zeeman sublevels, and in the ground state you have 2 Zeeman sublevels, which are labeled with the MJ minus 1/2 plus 1/2, as here you have just the choice between these two values. And here you have G prime equal to 3/2, so the levels goes from minus 3/2, minus 1/2, 1/2, and 3/2. So what you have to know here, that from this level, for instance, you can absorb sigma minus photon. You can absorb pi photons, or you can absorb sigma plus photons, but you have some coupling strengths for the different transitions, and these coupling strengths are related to the Clebsch-Gordon coefficient. And in the case of this transition, here you have a coefficient 1, but here you have a Clebsch-Gordon coefficient of 2/3, also square root of 2/3, and here you have the square root of 1/3. You all know the Clebsch-Gordon coefficients? Yes? Yes, okay. Yes, maybe one next. So this is the atom, and now the lasers. Instead of considering a sigma plus, sigma minus case, I will consider the case where you have the one beam which is linearly polarized along the x direction. So it is propagating along the z direction. And you have a contrapropagating beam in the minus z direction, which is polarized on the y direction. So you have two linearly polarized beam. Yes, maybe this is wrong, but doesn't matter. X, Y, Z. No, it was it was right. It is wrong in my notes. It doesn't matter anyhow. So I have a first field, electric field, which is EL divided by 2 exponential minus I omega L T, I think, plus E kz. I do not put any phase, and this one is AX plus complex conjugate. And the second field, E2, is, so they have the same intensity. Probably minus E k z. What did I do? No. I did that. Don't know why, but I did that. And for a reason that you will see later, I put an I here. This is just a trick to have a maximum of intensity when z equals 0. And so I have to compute the total field, which is E1 plus E2. And it turns out to be an I split exponential minus I omega L T from the exponential I k z AX plus I exponential minus I k z A y plus complex conjugate. And to go on, in fact, I will introduce the E plus field, which is E x plus E y, I E y divided by square root of 2, and another one, E minus, which so it may be not the exact standard definition of the, but this is a sigma plus field, and this is a sigma minus field. And so now you just have to reverse the expression, and you find that the total field is just something that is EL. Probably I have a square root of 2 divided by 2, and I have my minus I omega L t cosine kz times E plus E sine kz E minus plus CC and right. Which means that if I draw my field along the z-axis, when z equals to 0, it is simple. I have just a sigma plus field. So in 0, my field is sigma plus. If I move to lambda divided by, I always have a problem, to lambda divided by 4, I have now a sigma minus polarization. And if I go to lambda divided by 2, I have again a sigma plus polarization with a minus sign, but the sign you do not, it is not so important. And somewhere in between here, so it is lambda divided by 8, you have the same component on the sigma plus and sigma minus fields. And so this is a linear polarization, but it is linear neither along x nor along y. It is at 45 degrees, let's to say. And here you also have a linear polarization, but at minus 45 degrees. So in one case it is like that, in the other case it is like that. I never know which one is the which one, so, but it doesn't matter. Okay, so now when you put all these ingredients together, you have the couplings that are different for sigma plus and for sigma minus light, depending on the levels. You have intensities for the sigma plus and for the sigma minus component that depend on space. So all this, so you have coupling depending on sigma plus or minus, the polarization. You have the intensity for the sigma plus minus depending on position, so on z. And so all that gives you light shift depending on m equal plus or minus 1/2 and on the position z. So I think it is time to stop, because if I begin to write something, it will become too long. Any question? You have a question, but you don't dare. Hmm? Okay. On the value of m, which is plus or minus 1/2, and on the position, because the couplings are reversed. In fact, here you have from the minus 1/2, you have again the 1. the 2/3 and the 1/3 here. So if you exchange the plus and the minus and the polarization, you have the same system. Any other question? Yes.
I think it's simple, but I guess I'm a bit confused why you're starting with these like the linearly polarized fields, because you have like a circular polarization usually in MR, and I think it adds the same way, I guess, so you get the same stuff out.
So it's not exactly the same, because when I just had the two circular polarization, I have a resulting polarization which is linear, but the direction of this linear polarization which turns when you move along Z. You can also, so if you have a J equal 1 to G prime equal 2 transition, and you shine in a sigma plus and sigma minus light on it, then you have also another kind of subdoppler cooling mechanism. But they are slightly different. And you need 2 more levels to describe, to obtain it. So I prefer this system, which is in fact the simplest system that exhibits some subdoppler mechanisms. But if you really want, you can also compute that. In fact, in this case, you have a kind of helix for the polarization of your field, depending on Z. But you can simply choose to this. If you are at rest, you just consider that this is the good quantization axis. And at that point, when you consider you have just linearly polarized light, like that, which interacts only on these 6 levels. And this leads to light shifts that moves the levels differently. And in fact, you have the same mechanism as we will see on Monday, which is the correlation between the optical pumping and the light shift, which removes energy of the system. So here, if you now consider spontaneous emission and the branching ratio from here, you can come back here, or you can go there and there. If you start from here, you arrive here, and you can decay either here or there. And so if you just compute the rate equation, the optical pumping, you end up with more atoms here than there. And now if you just imagine that you were here at Z, and then you suddenly move. It means that, in fact, you have now to change the quantization axis, which means that you have to redistribute the population between the various sublevels. And you will have to, so it means that you will put some population from here to there, and then the optical pumping will have to draw back the excess population from here to there. And so it will reduce, the optical pumping will reduce the total energy, and so you will always take the energy from the kinetic energy of the atoms. Here it is simpler, because you have, in fact, when you have just the 2 sigma plus and sigma minus polarization, your system is just split in 2 B systems. So it is, you have 2 independent, for the light coupling with the lasers, you have 2 independent 3-level atoms, systems, not atoms. And so it is simpler.